Okay, picking up on calculus section 8.5, alternating remainder and conditional absolute convergence. So we want to use the alternating series remainder to determine convergence. So, and then in addition, we want to classify convergence as absolute or conditional. So remember, with alternating series, we have two tests really. That we want the limit of the term to be equal to 0, and we want the n plus 1th term, a sub n plus 1, to be less than a sub n. And so in that way, we can say that the alternating series, by the alternating series test, the series converges. Not that we know what the sum is. So we want to classify it with this as convergence being absolute or conditional. So alternating series, we start out with the remainder. If an alternating series converges, then the sum of the series can be approximated by the partial sum. The error associated with the sum is less than or equal to the first neglected term, or the n plus 1th term. This, to me, is absolutely fascinating that this happens. But so the remainder is the maximum error is the absolute value of the difference between the sum of the series and the nth partial sum being less than or equal to the a sub n plus 1th term. And if you look at the absolute value when we laid it out like this, let me say this is in purple. So we see how we have that. This is here and here, just like we do absolute value, solving an absolute value difference like we have. S minus S sub n is then in the middle between the two positive values in that inequality, three-part inequality. So then you get, in the end, you get S sub n, I'll put it in pink here. Here's S sub n on this side. Okay, S sub 4, S sub n, I put there, and S sub 4 here, but S sub n. And then we're going to subtract on the left A sub n plus 1, and we're going to add it on the right, since it is the error. Okay, so we have the expression that we need by adding S sub n to both sides of the n sides of the inequality. All right, so what we want to be able to determine what the sum is. So sometimes there's a reasonable number of terms to add up. If you're going to add up 1,000 terms, it gets to be fairly, not tenuous, what's the word I'm looking for, just exhausting, right? So in this example, you're going to approximate the sum of the alternating series. We want to use the fourth partial sum to approximate the sum of the series and determine a reasonable interval for the actual sum of the series. Is the partial sum S sub 4? So the fourth partial sum, an over or an underestimate then. So now for the first part of this, what we want to do is look at some of the terms. We want to lay it out, okay? And you can see when n is equal to 1, we have 1 over 1 factorial for the term. When n is equal to 2, you just kind of go right through it. Since you're starting, you always note where you're starting from. And so the fourth partial sum is listed there underneath that bracket, right? So now then that means the fifth term is then going to be used for the error. So the way we're going to work this out is we're going to be able to say the sum, according to this up here, oh, don't have a color there, according to that, then we can really just say the sum, the fourth partial sum minus the error is less than or equal to the sum, which is less than or equal to the fourth partial sum plus the error in this line. So we've got our sum laid out, and then we've got, that turns out to be on the left-hand side 0.616, repeating, is less than or equal to the sum is less than or equal to 0.63, repeating when we combine those parts of the inequality. So we have the range of what our sum should be, okay? So note that it has to pass the alternating series test, which it does. That the first one is that the limit is equal to 0, and that the n plus 1th term is less than the nth term, okay? So now when you look at this, what's going to matter, this is going to turn out to be an underestimate, because picture this sum is going to be bouncing back and forth between positive and negative, positive and negative. Since the last term is negative, that's going to pull it downward, so it will be lower than the actual sum. And that's all we need to say there. And then the error is going to be 1 over 20. Now the 1 over 20 is this term, the 1 over 5 factorial. That is the n plus 1th term, or the fifth term. So if we have a sub 5, that's going to be a sub 4 plus 1, and that's the one that turns out to be 1 over 120, and that will be our error. Okay, pretty cool. All right, then we have what alternating series partial sum will have an error less than or equal to 0.001. So what we do in this one is we say, okay, we've got a series here, and what I'm doing is I'm using a capital N, and when I solve for N, I'm going to try to solve for N when I can, and in this one, it's fairly algebraic, so I can do that. So just a reminder of what we're doing. We are setting the N plus 1, I should make it capital since I'm using a capital, the N plus 1th term. So I'm plugging in N plus 1, and I bring it down. I want to set it less than or equal to 1,000th. So when I do, down here as I'm coming down, you see that 1,000 then is less than or equal to 2n plus 1. Solving for 2n, I get n must be greater than 499.5 or 499.5. So I'm going to choose 500. So when n is 500, then the n plus 1 term is going to be my error, or the 501st term. So here's my partial sum. It gives an error, which gives an error of less than 0.001, and that would be the 501st term, which is the error. Okay, that's it for that one. Then moving over to the next one, sometimes it makes sense, especially with factorials, they get big very quickly. So in the first step for this, I do the same thing. I'm looking at the n plus 1th term. So for n, I'm going to plug in, here's n, let me get a different color here. Here's n, so I'm going to plug in n plus 1 for the n plus 1th term. So when I do, I want to set that less than or equal to 0.001. So I get 1 over the quantity n plus 2 factorial. I want that to be less than 1 over 1,000. And so I can write out some of the terms of this series, as you see, a sub 0 all the way to a sub 6, right? So what I'm looking at is the error, right? I want to know how many terms. So as it turns out, it's kind of weird when you say this because you have an a sub 0 here, but it's going to be the 5th partial sum, even though it's the 6th term. So I'm going to need 1, 2, 3, 4, 5, 6 terms to get to a sub 5, okay? So when I do that, as I'm adding them up, you see the alternating sign going in. When you have a sub 1 is when n is 1, so I get 1 over 2 factorial, but the sign is negative in front of it, and so on. 1 over 2 plus 1 factorial, so that's 3 factorial for a sub 2. And as you look across there, what you can do is realize that factorials grow very quickly. So one of the things that I do is if you take a look at this arrow here, I kind of like to fool around with this and say, all right, well then 1,000 is less than or equal to n plus 2 factorial, just doing a mathematical manipulation. Multiply by 1,000 and multiply this inequality by 1,000 and n plus 2 factorial. So that in that you get this inequality. So then I just plug numbers in, and you can see it's not going to take too long for you to discover, oh, I'm over the top with this, right? So you've got 5,040 is when n is equal to 5. So you're already way above. But n equal to 4 is not bigger than 1,000, so you're not quite done there. And then you can see you could handle it like this, algebraically, like I just did with this table. Or you could take each term and you could say, all right, let's look at each term. And if you notice the 1/2, 1/6, 1/24, 1 over 120, 1 over 720, you're still not to that less than or equal to 0.001, 1,000. So you got to go one more term out after the 1 over 720 to get to the 1 over 5,040. And you can see that you have the same thing in both the tabular values that I have here on the right, and then this last value. That is less than 0.001. So a couple ways to do this, but S of 5 is the partial sum. And forgot the word sum. So partial sum, and the error is the next term, the a sub 6th term, a sub 6th term, a plus a sub 5 plus 1. And that's going to be 1 over, and it is negative there, 1 over that, okay? It is minus. Okay, so that last term is the error in yellow, as I said. Okay, so then we have another problem here where we're looking at error, but in a slightly different way. So in this one, given it's supposed to be a polynomial function, right? P sub n of x. So in this one, you've got this series. It's an alternating series, and it's asking what is the smallest number m for which the alternating error bound guarantees that the absolute value of f of 1 minus p sub 4, which is the fourth partial of 1, is less than or equal to m. So the first thing that I would do is I'm letting you know that f of k is that function in there that is actually the sum. So if we have a sum in here, what I want to do is take and say the parts of this. If you notice, I have x is equal to 1 and k is going to be equal to 4 in this as we look at our terms. And so the actual sum is going to be f of 1. Okay, and with this, the polynomial is going to approximate the sum. I think I'm going to change this to the a sub n, but I'm going to make it an a sub k, okay? All right, so f of 1 is the actual sum. P sub 4 of 1, the fourth partial sum, I have the difference in the absolute value is less than or equal to m, where m is the error. So what we need to do is just say, well, the error will come, therefore, the error comes from the fifth term. The next term, right? So 4 plus 1 from the fifth term. So P sub 4 of 1 is the fourth partial sum at x is equal to 1, because the sum is for f of 1 minus the fourth partial sum such that k is going to be equal to 5. So here, I'm sorry, k is going to equal to 5 for this. So with the fourth partial sum, let me change this here. K is going to be equal to 5 for this particular problem. So we've got negative 1, it's going to be to the fifth power, right? A sub 5 that we are interested in, right? So we're going to take our a sub k up top that we have here, and we're just going to plug into it. So we get negative 1 to the fifth, negative 1 to the fifth. We want to see what this term looks like, times 1 to the fifth over 5 squared plus 5 plus 1. And when we combine that, we get, what do you get? Negative 1 over 31. So this is our error. So the smallest number for m for which the alternating error bound guarantees that that happens is 1 over 31. 1/31st, okay? And that is our error. Okay? So there is that one. And now for the rest of the story, I know you may have watched a video on this, and I just want to double back on this and make sure that it's clear. So if we're looking at this, one of the things I usually do is kind of lay out a few terms just to get comfortable with it. And then I look at the series and I try to break it up. If you see in green in both of these, I have the a sub n terms. So you can see the a sub n in this first one, this one is then going to be 1 over n to the 2/3, right? And the a sub n in this one is going to be the 1 over 3 to the nth, okay? So with the first one, I've got my terms laid out, and I'm going to look at that and I'm going to say, looks like a p-series, right? So that P series would look like this, and it would say, here we're testing this. This would be the summation of 1 over n to the P. And notice that P here is equal to 2/3. So in this, we're going to say it diverges by the P series test. If you recall, it's between 0 and 1. P is between 0 and 1, so the series is said to diverge. I should put this stuff in there too. So we start out like this. We look at the a sub n term, diverges by the P series test. Okay, so then we look at the alternating series test and we say the limit as n approaches infinity of 1 over n to the 2/3, and that turns out to be equal to 0, of course. So check that off. So that's part of the series test. And then we also have, is a sub n plus 1, is it less than or equal to a sub n? And in this case, you have 1 over the cube root of n plus 1 squared. That is less than or equal to 1 over the cube root of, the 3 there, of n squared. And now you can actually prove this out. You can cross multiply, and I'm going to leave that up to you guys to handle. But here's what we say about that. Once we get this far, then we're going to say, therefore, the summation, since everything passes the alternating series test, and we know that this is the P series test, we know that the original series diverges, then we're going to say the summation of -1 to the nth power over the cube root of n squared, from n is equal to 1 to infinity. It converges, and it's what we call converges conditionally. So it converges conditionally. So here's what you're going to remember is that if your a sub n term, or it's really the absolute value of the term of the series, including the negative, if the a sub n term diverges such that the summation from n is equal to 1 to infinity of a sub n diverges, then the series converges conditionally. Okay, it converges conditionally then. Okay, so there's that one. So kind of categorizing what these look like. The term diverges normally without the -1 thingy, but so then we would say the series by the alternate series test converges. We say it converges conditionally. So, and then for the second one, we lay out a few terms there, see what it looks like. It looks like, and sometimes what I'll do is if I have an expression in here, I'll kind of factor that out, and it's easier to input the values and get a few terms. And then I look at the a sub n term, it's 1 over 3 to the n. So then I'm saying this is going to act like, this is a geometric series, right? Looks geometric. Kind of shortening that, looks geometric. Okay, so with this one, we would then say, oh, yeah, this is when we have the summation of r, right? R from n is equal to 1 to infinity. It's going to be an r to the nth term. And in this case, it's going to be 1. Remember, it's 1 over 3 to the nth, right? So this one converges. So it converges where 1/3 is less than 1. Okay, so it's going to converge. And so, and we could put an absolute value around there, but not necessary at this point. So then with the alternating series test, we're going to say that the limit as n goes to infinity of It's just the a sub n term we're dealing with. 1 over 3 to the nth, that must be equal to 0, which it is, check. And then we're going to say that the a sub n plus 1 term has to be less than or equal to a sub n. So you're looking at this where you have 1 over 3 to the n plus 1 term is less than or equal to 1 over 3 to the n. And in the same way, we could do this out. We could solve this algebraically. Very easy to cross multiply and get your 3 to the n's separated and divide them out. But we won't do that right here. All right, and so then we make a conclusion here. Therefore, this series, we would say, from n is equal to 1 to infinity of -1 to, it's the original one, -1 to all this stuff, n squared plus n over 2. That's all in the exponent. You got to be careful with that sometimes. And then it's over 3n, It converges, what we say, absolutely. And it converges absolutely. Nice fit. Okay. And in that one, we're going to say, get the rectangle, no rectangle right there, right? Okay, try it one more time here. I'm not going to, there we go. Okay, so we have, so it converges absolutely. So the a sub n term here converges. Here's when you tell that it converges absolutely. When the a sub n term, I guess I should say when. So with this, when the a sub n term converges such that the summation of a sub n converges, the series is said to converge absolutely. Converges absolutely. And it's very definitive. Either both the alternate series and the absolute value of the series, both of them, the positive, normal, geometric series and this series converges absolutely then. The series converges absolutely. So that's it for this lesson. I think that's 8.5 in a wrap. I have a couple more problems. I think there's one more in the folder for today. And so I'll let you examine that one as well. And I'll see you tomorrow and we'll pick up with the ratio test. Have a good day.